All right, so we've been focusing on the gradient vector, and we showed how the gradient vector can be used for a couple of things so far. We showed that the gradient vector can be used in a formula for determining the directional derivative of a function in whatever direction we like. But we also showed that if we want to maximize that directional derivative, that the unit vector that will maximize the rate of change is always going to point in the same direction as your gradient vector, and then the magnitude of that gradient vector is going to give you that maximum rate of change. But the gradient vector has even more interpretations that are also really useful in a more geometric context. So we're going to talk about that next. Let's suppose that we have a function of three variables. And when we defined functions of three variables back in section 14.1, we talked about how you could represent graphs of those functions using level surfaces. Remember, level surfaces always have the form f of x, y, z, so your function of three variables, equals some specific constant. It's taking that function of three variables and picking specific constants to set it equal to determine surfaces that we call level surfaces. So let's suppose that we have a level surface to this three variable function. It looks like this as an equation. And let's pick a point that lies on that surface, x naught, y naught, z naught. We're going to call that point P. Okay. Then we're also going to let C be some curve on that surface that passes through that point that we just selected. I'll show you a picture of that down here in a minute. Actually, let's see if I can get that picture up here. Here's part of it. So if we look at this blue surface here, that's S. We have our point P right here, and then a curve C that passes through that point P. Okay? Now, because C is lying on a surface in 3 space, it's a space curve. That's technically what it is. And it would be given in the form of a vector function, r of t equals x of t, y of t, z of t. This is now kind of bringing chapter 13 into the mix, where we talk about space curves and vector functions. Because this curve C passes through that point P by assumption, then there is some value that I could plug into this vector function. Let's call it t naught. That would give me the point P. So we're going to say that t naught is the parameter value corresponding to that point P. Okay. Now, because C lies completely on S, then if I were to substitute this vector function into the function capital F, it should come out to K, because that's necessary of all points that lie on S, and C lies completely on S. So writing it in that form, I could say f of x of t, y of t, z of t is equal to K. All right? But notice what I did. On the left-hand side, I've written this function in the form of a composition of functions. So this is representing the three-variable function f as a function of the single variable t. And this makes me think of what we did with the chain rule in the previous section. If I differentiated both sides of this equation with respect to t, my right-hand side is a constant, so it's going to go to 0. My left-hand side, I would need to use my chain rule on, and that gives me this. Okay? But notice something about your chain rule. The chain rule, any version of the chain rule, gives us something that looks suspiciously like the result of a dot product. So I want to see if I can take this expression from my chain rule and write it in the form of a dot product. So let's look at some of the components here. Partial of f with respect to x, respect to y, respect to z. That's showing up as the first factor in each of these three products. I can call that fx, fy, and fz. If I take those three in a form of vector from those, that would be the same thing as the gradient of f, wouldn't it? Because that's the vector that has those three partials as its components. What about the other partials? dx dt, dy dt, dz dt. Well, those would be the components of r prime. Because remember, x, y, and t as functions of t, x, y, and z as functions of t are the components of my vector function r. And so back in chapter 13, when we talk about how to differentiate those vector functions, dx dt, dy dt, and dz dt are exactly those components. So that shows that this expression up here has this form, del t dot r prime of t equals 0. And in particular, if we're interested in what's going on at that point P right there, I could plug t naught into this expression on the left, giving me the gradient of f at x naught, y naught, z naught, dotted with r prime of t naught. Remember, plugging t naught into the t's here should produce x naught, y naught, z naught, which is why we're seeing that here. So the gradient of f at that point dotted with r prime at the parameter that gives us that point is equal to 0. Now this should look very, very familiar. Something should occur to you here. What does it mean when two vectors have a dot product equal to 0? From chapter 12, we know that that means that those vectors are orthogonal to each other, or perpendicular. Now let's think, what is r prime of t naught geometrically speaking? Well, again, in this picture down here, we have that curve C, which is that space curve that r of t represents, and r prime gives us a tangent vector to that curve. Again, chapter 13 is where we learn that. Specifically, r prime of t naught would give me the tangent vector to the curve C at the point P. And what we're learning here is that the gradient vector, del f, is perpendicular or orthogonal to that tangent vector. Okay, but it gets a little bit more interesting than that, because the space curve C lies completely on the surface S. And it's not too hard to see that the tangent vector r prime has to lie completely in the tangent plane to that surface. We talked about tangent planes in 14.4. It has to lie in the tangent plane to the surface S at the point P. So what that tells us is that del f, the gradient of f at P, is orthogonal to that plane, that tangent plane. That means that the gradient vector can be used as a normal vector to that plane, which means it's going to make an appearance in the equation for that plane. You remember in chapter 12, we talk about how to come up with the equation for a plane using a normal vector. So with that in mind, we see that the equation for this plane, because we have a normal vector now, del f of x naught, y naught, z naught is a normal vector for that plane, and we have a point contained in that plane, the point P, x naught, y naught, z naught. Remember, that's all you need for the equation of a plane. This is what that equation would look like. Fx times x minus x naught, Fy times y minus y naught, Fz times z minus z naught equals 0. That's that standard form for the equation of a plane. Remember also that we talked about normal lines to a plane, which is a line that passes through a given point and is orthogonal to that plane. This relationship, the fact that del f is orthogonal to the plane, means that this vector is actually a direction vector for the normal line passing through P. So with that said, we can easily come up with symmetric equations for that line using what we know about symmetric equations from chapter 12. It would look like this: x minus x naught over fx equals y minus y naught over fy equals z minus z naught over fz. That's the equation, symmetric equations for the normal line to S at that point P. Okay, so to wrap things up here, let's use these in an example. I want to find the equations of two things: the tangent plane and the normal line to the surface given by this function, this equation, x equals y squared plus z squared plus 1, at this point here, 3, 1, negative 1. Okay? Based on what we're seeing here, in both of those equations, both from my tangent plane and from my normal lines, the equation of my normal line, I need fx, fy, and fz. Remember, those are the components of my gradient vector. So let me compute my gradient vector first. What is del f equal to? Well, I don't know what f is yet, right? So let me actually back that up a second, because this is an equation, but where did the function capital F come from in the first place? It came from writing this function in the form this equation in the form f of xyz equals a constant, right? So what I need is to have this equation in the form where all of my variables are on one side and a constant is on the other side. We can make that constant 0 to give us kind of a quick way of doing that. Notice this equation is equivalent to 0 equals y squared plus z squared plus 1 minus x. I'm just subtracting that x from both sides. And this guy is what I can refer to as f of x, y, z. Now, before we go any further, I want you to notice that you could subtract this 1 over here, and you would still have the correct form for this thing, because all the variables are still on this side. So I could have a different function that I'm calling f. But that function will only differ from this function by a constant, and the purpose of finding f is to find its gradient. When you find the gradient, that difference of that constant is not going to matter. The gradient will still be the same. So you don't need to worry about having the correct constant over here. In fact, by default, you might just want to always make it a 0. Now we can find del f. What is del f? Well, I need my partials with respect to x, y, and z. So my partial with respect to x would be -1. Partial with respect to y would be 2y. And with respect to z would be 2z. Okay, and now we need that partial, we need that gradient with gradient at a particular point, 3, 1, -1. So what is del f of 3, 1, -1? Well, that would just be plugging these values in for x, y, and z here. -1, 2, -2. That's what that comes out to. Okay. Now, I need the equation of my plane. But the fx, fy, and fz, those are just the components of my gradient vector here. So that's fairly straightforward. I have all that stuff. And then the rest of this just looks like the equation of a plane. So let's get the equation of my plane first. I'm going to have -1, so negative x minus x naught. What is x naught? It's 3 plus 2 y minus y naught, which is 1, plus -2, so let's write that as -2, z minus z naught, which is z plus 1, and that's equal to 0. So that's the equation of my plane. I could write that in a slightly different form, though. So I could distribute the negative in here. I could say that that's equal to -x. This would be plus 3. Let's deal with that at the end. -x plus 2y minus 2z equals. So let's see. This would give me a -3. So that's +3 minus 2. So we're up to 1 now. Minus 2. Again, it's -1. If I add that 1 to both sides, I would get just 1 here. So that's one way of writing the equation of this plane. Let's go like that. Sometimes people like to have a positive coefficient on your first term, so I could also multiply everything by -1 to change the signs. It doesn't really matter. There's different ways of expressing this same equation. This is just the way I'm doing it here. Next up, we need the equation for our normal line. Well, we already have everything that we need for the equation of our normal line, because again, it looks like we just need x minus x naught, y minus y naught, z minus z naught, fx, fy, fz. All the same things that showed up in the equation of our plane, but just, written differently so that it looks like symmetric equations. So we're going to have, here's my x minus x naught, x minus 3 over fx, which is -1, equals y minus y naught, which is y minus 1, over fy, which was 2, equals z minus z naught, which is z plus 1, as we've seen, over fz, which we got -2 for that. And there we have the equation, symmetric equations for a normal line. Okay, that's going to wrap it up for 14.6.